Hello everyone, welcome back. This is Ritkul again, and we have been getting some doubts regarding the graph centrality examples and how to solve the graph centrality measures which we studied in class practically. So I'm going to take this short session and hopefully this would help you understand how these examples can be solved in practice. Uh, During the class, we studied three different types of centrality measures, which is degree centrality, closeness centrality, and betweenness centrality. I'm going to take an example of each in this session today. So let's start with degree centrality, which is the simplest. To make this example wholesome, I've taken a directed graph here. This is just an example graph where you have 1 to 2, 2 to 3, 3 to 4 and 5 to 4, and there is a double pathway from 1 to 6. Now, in this example, every edge which is marked with this red highlight is an outgoing edge, and every edge which is marked using this green highlight is an in edge, which is, let's say we take the node number 1, we see there is one in edge and two out edge, so there is out degree of this node becomes 2 and in degree simply becomes 1. Now, have an assumption where this graph was undirected and essentially there was just these three nodes. In that case, the degree would be 3. Okay. Now, we can do this for each node. So, for 2, there is one incoming and one outgoing. So, 1 and 1. In case this was undirected, it would become 2. For the case of 3, there is one coming in from 2 and going out to 4 and 5. So 2 out and 1 in, total 3. On 4, there are only 2 incoming edges and no outgoing edges, you can see. So the out degree becomes 2 and in degree becomes, so out degree becomes 0 and in degree becomes 2. 5, there is one in, one out, so 1, 1 each. And then on 6 again, there is one outgoing and one incoming, so 1 and 1 each. There is an exception to be made here, which is assuming this graph was undirected, all other nodes would be same, but then you would not need two edges between 1 and 6. There would be just one edge which you can go back and forth because it's undirected edge. In that case, essentially these two edges would convert into 1 and the total degree would only remain 2. And in the case of 6, these two would also converge into 1 and the total degree would become 1. However, in this example, because it's a directed or undirected graph, this is a directed graph, we would have to count these two separately. In general, degree centrality is one of the easiest to calculate, where every time you're given a graph, you just zoom in into the node which you want to calculate, kind of like this which I've done. You don't need to always make these figures in an example to calculate. These are just for illustrative purposes, and then you can just count different kinds of edges which are going out and in. Okay. Next, we go to closeness centrality. And both for closeness centrality and betweenness centrality, there is an important path. The important thing which needs to be known is that you should know the shortest path between two nodes. Now, calculating shortest path in itself is a well-studied problem. There are different methods of doing it. Generally, for centrality measures, you are required to find the shortest path between all the different pairs of nodes. And the standard way of doing it is using something called a Floyd-Warshall algorithm, which you would have studied in your data structures and algorithm course. So the way I like to do it before I start solving any example of closeness centrality or betweenness centrality, I just I do a dry run of Floyd-Warshall on the entire graph and get the shortest path of all the nodes. If it's a very small graph, you can also do all of this heuristically. You don't need to dry run the algorithm itself, but a better way would always be to dry run the algorithm so you never miss any possible edges. In case of this very simple graph, I take all the possible pair of nodes pass by pass and then try to find the shortest path between them. A point to be noted here, in order to make it more wholesome, I've made this graph, this is the same graph as before, but previously it was directed. Now I made this graph undirected, so it's easier to understand. There is a slight difference if this becomes a directed graph, and I'll discuss that difference later. But assuming this is an undirected graph, first let's say we try to find the shortest distance between 1 and 2. And as you can see, there is only one path to go to 1 and 2, which is 1. You can directly go from 1 to 2, so length becomes 1. Then for 1 to 3, there is again only one path. You can go 1 to 2 and then 2 to 3. So the length becomes 2. Now when you want to go to 1 to 4, there are actually two different paths you can take. 1 to 2, so you can go 1 to 2, 2 to 3 and then 3 to 4. Or you can take 1 to 2, 2 to 3, 3 to 5 and 5 to 4. Of course, the first one, which is 1, 2, 3, 4 is the shorter one. So the length is 3. In the same measure, I find 1, 5 and 1, 6 also. Now you find 2, 3. The important difference between a directed and undirected graph, which I was talking before, is you have started doing 2, 3 now. You did not do 2, 1 in this case. Because it's an undirected graph, the distance between 1, 2 and 2, 1 would be the same. However, if this was a directed graph, that changes and you would have to calculate 2, 1 separately. There is no magic in solving that. You have to solve it the way you just did. It's just the calculation reduces for a directed graph, for an undirected graph. And if you are doing it by running the Floyd-Warshall algorithm, you anyways don't have to care, because the algorithm in itself takes care of both directed and undirected graphs, and you will just get the distance. So I do this dry run for all the possible pairs, and once you do all these possible pairs dry runs and you get all the shortest path, you can end up with this very neat matrix, which is all of these are nodes and all of these are nodes. Of course, the distance between the diagonal is 0, because distance between 1 to 1 and 2 to 2 is always 0. And then all these distances are the values which we just calculated above. So distance between 1 and 2 is just the one which we calculated here, which is 1 to 2 is length 1. And of course, it's a symmetric matrix if you look at across the diagonal, because the distance between 1 to 2 is the same distance as 2 to 1. Once you have the shortest distance table, calculating centrality is actually pretty easy, which is if you want to call closeness centrality for any given node, the formula is n minus 1 over summation of all the distances, all the shortest pair distances from that node. Now, if you go online and study, you would see different versions of this. So this is essentially a way to find a normalized centrality. Now, sometimes you would see not n minus 1, but only n in the numerator. That is because if you are doing it on a very large node, the significance of n minus 1 kind of reduces, and n minus 1 can be approximated to n. You would sometimes also find 1 over this. That is a method of trying to again another way of just normalizing the difference. It doesn't really matter which one you are using, as long as you are consistent in using it across all the wherever you are considering the measures. Just be consistent. But the most popular one and the basic one is n minus 1 over summation. So let's say now we want to calculate closeness centrality for graph node number 1. It's just we have total nodes 6, so 1, 2, 3, 4, 5, 6. So we do 6 minus 1, and then we essentially just take this row and sum all the elements of this row. So 1 plus 2 plus 3 plus 3 plus 1, and you end up with 5 by 10, which is 1 by 2. For second, again the numerator stays the same for all the nodes. However, the denominator now just becomes sum of this row, which is 1 plus 1 plus 2 plus 2 plus 2. And similar way you can do for all the nodes here, and you get the closest centrality for everyone. Now, betweenness centrality is again a counting centrality like degree centrality, but here the count is not the number of edges coming in or out. The count is that if you take all the possible shortest paths which are present, in how many shortest path the given node is present. So the way of doing that is I take all the possible shortest paths which are present. So 1 to 2, 1 to 3, 1 to 4, 5, 6, then 2 to 3, 4, 5, 6. Again, we are not considering 2 to 1, because that is same as 1 to 2. If this was a directed graph, we would be counting that separately. Okay, we get all the possible paths, and I write down all the possible shortest paths, all the shortest paths which are from like whatever is the shortest path from 3 to 6, from 4 to 5, from 2 to 4. These shortest paths are the same shortest path which I found when I was calculating this table. Again, you can get the shortest path by making the Floyd-Warshall algorithm. The basic dry run of Floyd-Warshall algorithms only gives you the distance, which is this metric. But because it's a dynamic programming algorithm, once you have this metric, if you backtrack this metric, you can also get the path. Again, that is something which is very typically discussed in a data structures and algorithm class. I hope all of you are familiar with it. In case that is not the case, please post it on the forum and we'll try to make another tutorial for that. Yeah. But yeah, you write down all the betweenness path. Now the important point to be noted here is you only count a count of a node is only counted when it is between the path. So not the edges. So when you are counting, let's say 1, 2, 3, 1 and 3 is not counted. Only the paths which are between the target and the destination, the starting and the destination node, they are counted. So a neat visual way of doing it, which I like to do, is I write all the shortest paths and I make this like red box, which excludes the starting node and the ending node. And then everything which is inside this red box needs to be counted. So now let's say I want to know the betweenness centrality of 1. I just count that how many times 1 occur in this red box, and I see 1 occurs once, twice and thrice. So the betweenness centrality becomes 3. For 2 it is 1, 2, 3 and then 4, 5, that is why it's 5. Again for 3 it's 5, and if you see node number 4, 5, 6 never show up in this red box, that is why their betweenness centrality is a 0. And that is how you calculate the betweenness centrality of a graph. To summarize, we looked at degree centrality. In this case, we looked at a directed graph example where you can sort of say almost zoom into a node and just count what is the number of edges coming out and going in. If this was a directed graph, you just count the edges. You don't really care about if they're coming in and going out. Undirected graph, you don't care if it's coming in or coming out. In case of directed graph, you have to count them separately. Then we looked at, for an undirected graph, we look at the difference. We looked at an example for closeness and betweenness centrality. The first thing for both the centrality calculation is you need to get all the pair of shortest nodes. So you want to get the exact path and the length of that path. You can get both of these things from Floyd-Warshall algorithm. Floyd-Warshall algorithm dry run would give you this matrix, and once you backtrack this matrix, it would also give you all these paths. And once you have all these paths, for closeness, centrality is just number of nodes minus 1 divided by, for each node, it's the sum of the row of that node. And for betweenness centrality, you can write all the shortest paths, ignore the starting node and the end node, and just count the number of times any given node exists in the middle in the pathway, and that gives you the betweenness centrality of it. I hope that makes it clear. Another thing is the examples given in this document for closeness and betweenness centrality are undirected graphs. The only difference with directed graph would be, so right now let's say the distance between 3 and 4 and 4 and 3 is same, but in case of directed graph that is not true and you have to calculate it separately. Again, Floyd-Warshall algorithm would take care of it as long as you run the algorithm the way it's supposed to be. There is no any special steps you need to take it. The disclaimer is just for the cause of this example. But yeah, thank you. If you have any doubts, please post them on the forum. I'll try to answer them. Hope you have a good day. Thank you.